Well, today I had a problem that kind of interested me, and it had to do a lot with internalizing what moment of inertia is. It made me think a lot about moment of inertia can be calculated. One thing that helped me to do this, or like to solve this, was David Morin's book, which goes into a problem pretty similar to this one. Prerequisites for this, I'd say, knowing a lot about moment of inertia. But at the very least, you need to know what a moment is and how to use the parallel axis theorem and how to add different objects together to calculate their net moment inertia. Okay, so here's the problem. It is from the 2016 FM exam problem 24. The moment of inertia of a uniform equilateral triangle with mass m and side length a about an axis through one of its sides and parallel to that side is 1 over 8 ma squared. What is the moment of inertia of a uniform regular hexagon, mass m and side a, with an axis through two opposite vertices? Okay, so here we have a hexagon, and typically what you hear from people is that hexagon is just 6 triangles put into a single thing. So if you don't know that, then this problem would probably be really hard to figure out. We get that the side length of this is a, and then the net mass would be m. Each of these little triangles would be m over 6. So we're given the moment of inertia for a triangle, an equilateral triangle around this axis. We're letting it rotate around here. It's saying the moment of inertia for this is 1/8 ma squared. In the hexagon, we're rotating around this, which brings up a little bit of confusion. So you do have triangles here, which are rotating around this, but instead, through the center. And then these two specifically are rotating just around the vertice of the triangle, not the edge. So I think this is a good application for what we call the parallel axis theorem. So what we want to do, with at least for the two in the middle, are move the axis here. Okay, so here we have the parallel axis theorem. You notice that it needs a center of mass, which means that we can't just go from here straight to here using whatever distance that is. So we have to find the centroid, find the center of mass, like the inertia of around the center of mass, and then we have to recalculate for the edge, basically. So what is this distance? There's not a lot that we can go off of, but we know that a centroid is the same, for an equilateral triangle, is the same as taking the perpendiculars at each side. When you take the perpendicular at this side, you're splitting it into 2 because it's isosceles. These are both a over 2. And then notice this is 30, this is 90 degrees, and that this one splits it into 2 because these two triangles are the same. So you get 30 and then 60, so you have a 30, 60, 90 triangle. So then to find the length of this, which is the distance you're trying to find, well, this is a over 2, and whatever this is, you multiply by square root 3 to get this. Length times square root of 3 equals a over 2. So then the length equals, after simplifying, square root a root 3 over 6. So then that's the distance that we have to plug in for h. So if we square this, we get, okay, so we have m times 1/12 a squared plus the center of mass is equal to the initial one, which is 1/8 a squared m. So then if we simplify, or we could take the least common denominator of both of these, we'd get 3 over 28 here, or 24, and we get 2 over 24. So we subtract and we get 1 over 24 a squared m equals the moment of inertia around the center of mass. Now that we have that, we use the parallel axis theorem again to find the other part. So what's the length of this? Well, all the triangles here are the same. So if we have the length of this, we know it's just twice the length of this for the bigger side. For the smallest side is half the length of the biggest side in the 30, 60, 90 triangle. So the new height would be h is equal to 3 times 2, which means you get root 3 over 3 times a. So we have IV for the vertice. Take the ICM of inertia around the center of mass. So let's convert all of these. So we don't know IV, we're calculating that. It's equal to ICM 1 over 24 a squared m times this squared. So the 3 on the top, it's turned into a 3, 3 on the bottom is turned into a 9 at 1/3 a squared. Finally, after simplifying all this, we get 3/8 ma squared equals IV. Now, this is just the first part of the problem. So now we have to look at the original hexagon. There are 2 sides that are pivoted by the axis, by their vertices, and then 2 sides that are normal, pivoted by the edge of the triangle. Now let's just calculate it for the vertices first, because we just found out the IV. So IV equals 3/8 ma squared. So if we were to calculate for both of these, don't forget the mass is 1/6 of it, because it's evenly distributed. We get 2 times 3/8 m over 6 squared. And then we add on the other 4, which is 4 times, and we already know these the angular momentum of these, which is 1/8 times m over 6, don't forget, a squared. Okay, I cleaned up the board so we can finish solving it. So IH, I'll say it's I hexagon. The moment of inertia of a hexagon. Let's simplify this. 3 and 6, that gets turned into a 2, and then this 2 cancels with that 2, so we get 1/8 ma squared. Here, the 4 cancels out with the 8, and we just get 1/12. This common denominator was 24, so we get 3 over 24 a squared plus 2 24ths. Ma squared is equal to IH. We end up with our final answer, IH equals 5 24ths ma squared, which is answer B. This is probably one of the most problems where you need a lot of moment of inertia knowledge, although nothing really else about rotation, and you need a little bit of math knowledge to know how to find the center of mass of the triangle, because you can't just go from end to end. I'd say this is one of the harder problems, so yeah, all right, see you.